Okay, this is lecture 10. Due to my business trip to Japan, attending an international conference, CSPAD, lecture 10 was recorded. Instead of starting a new topic in this lecture, I just wanted to introduce some selective papers. More specifically, selected papers from the International Electron Device Meeting, IEDM, will be introduced. These papers are selected from the modeling and simulation sessions. Well, the selection has been done completely based on my personal view, so it would be very subjective in a sense. First of all, you must understand that I don't know the prehistory of TCAD, as my career as a graduate student started only in 2001. Works in 1980s or before cannot be discussed. Also, my major research field is the device simulation. Therefore, the papers about the process simulation are not included. More importantly, some trendy topics are not included or less emphasized in this lecture. 2D materials, new memory devices, and ferroelectric devices have been very hot topics. The first one by Professor Fabrizio Bonanni is selected because it is closely related with my PhD dissertation. In the electronic devices, even when the DC bias voltages are applied, time-varying currents are observed. It is called noise current. Since the electronic noise determines the minimum signal, prediction of electronic noise is an important task. Although a general way to calculate the electronic noise was known, even at 1995, it was too much time-consuming and impractical. This paper by Professor Bonanni clearly solved the problem. Inspired by a technique used in the circuit analysis, he proposed a very efficient and practical way to calculate the electronic noise. This paper by Professor Arsen Arsenov is about the random dopant fluctuation. Although we consider the dopant concentration at a certain position, actually this quantity represents an average number of dopants in a small volume at that position. For small devices, the number of dopants is not that high. For example, consider a cube whose edge length is just 10 nanometer. Then, how many dopants are found with the dopant density of 10 to the 18 per cubic centimeter? The answer is 1. Now consider several cubes with the same dopant density. For some cubes, there is no dopant at all. For other ones, we can find a single dopant. For other cases, we can find multiple atoms. Since the number of dopant atoms is different, electrical properties of these cubes will be also different. This paper discusses the randomness originated by the dopant distribution. Professor Jungemann was my boss when I was a postdoctoral researcher. As I explained earlier, Professor Bonanni suggested an efficient way to calculate the electronic noise. However, the method was applied only to the drift diffusion model. In this semester, we will study the drift diffusion model. Its limitation is well known, and the hydrodynamic model is regarded as an improved model. In this paper, Professor Jungemann applied an efficient noise calculation method to the hydrodynamic model. Parameters of the hydrodynamic model were extracted from the Monte Carlo method. Professor Matthew Luigier is famous for his contribution to a rigorous quantum transport simulation. The quantum transport is the most accurate way to consider the carrier transport. However, it is difficult to include the scattering mechanisms. Therefore, many simulation results are reported without considering any scattering mechanism. It is called the ballistic transport. Of course, in the realistic cases, we must consider those scattering mechanisms. In this paper, the phonon scattering is included. Since the atomistic structures were considered, for every case, the phonon dispersion relation is newly calculated. The tight binding Hamiltonian was used for the electron transport. Dr. Karlov of TU demonstrated that we can solve the Boltzmann transport equation directly for three-dimensional devices. Spherical harmonics are used to describe the momentum space. Basically, it is a matter of computational efficiency. I have reported some results for two-dimensional devices, and the method can be applied to three-dimensional devices too. However, it would be very computationally heavy. In this paper, Dr. Loop suggested some methods to reduce the computational burden. One is to use an unstructured mesh. Another one is to use a position-dependent expansion order. Simply speaking, these methods are trying to increase the computational accuracy only for an important area. For MOSFETs, of course, the important area is the channel region. Although a direct solution of the Boltzmann transport equation can be obtained, one important physical effect is missing in the spherical harmonics expansion method. It does not consider the quantum confinement effect. In order to overcome this shortcoming, the multi-subband Boltzmann transport equation is solved instead. In this paper, Dr. Sung Jin of Samsung Semiconductor Incorporation reported such an attempt. In 2014, people felt that the silicon channel cannot be used in more advanced nodes. As alternative channel materials, indium gallium arsenide for N MOSFETs and germanium for P MOSFETs were investigated. The left figure shows the electron density and the red color means higher electron concentrations. The quantum confinement effect can be clearly visible. The right figure compares simulation result with or without scattering mechanisms. Since people felt that alternative channel material were required, several works on the 2D material has been reported. This paper by Professor Luigier's group is a representative one. It is not convenient to build a tight binding Hamiltonian for a 2D material because simply there are too many 2D materials. Therefore, the Hamiltonian obtained from the density functional theory, DFT, is directly used to calculate the IV characteristics. In this paper, MOS2 is considered. However, we can find many other papers where different channel materials are considered. Neuromorphic devices are investigated actively worldwide. In many cases, these devices were originally developed as alternative resistive memories. However, compared with the conventional memories, they suffer from some practical difficulties. Instead, these resistive memories can be employed as neuromorphic devices. More specifically, they can be used as synaptic devices. This paper is not directly related with the TCAD simulation. Instead, from a collection of measured data, the authors found that any synaptic device can be modeled with the conductance versus pulse characteristics. Then, using this unified description, they calculate the performance of the entire array. Although it is not in the scope of traditional TCAD, nowadays the coverage of device modeling is expanding rapidly. Eventually, the overall performance of a system should be improved. We have seen that the DFT Hamiltonian is used in the quantum transport simulation. In many cases, the gate oxide layer is excluded in the transport simulation. Of course, it is mere an approximation. In this paper, Professor Minchen Shin of KAIST included the gate oxide layers in the simulation. Various silicon dioxide layers, beta cristobalite, alpha quartz, and amorphous are considered. It was found that the on current depends on the gate oxide layer. The amorphous result is similar with that of the alpha quartz. On the other hand, beta cristobalite result is different. Including the gate oxide layers increases the computational burden significantly. By adopting an efficient method, Professor Shin reduced the number of basis functions considerably. Now, AI. This paper by Mr. Sang-Hoon Myung of Samsung reported their real-time TCAD framework. In this approach, a neural network is trained with the TCAD simulation result. The electron and hole densities and terminal current can be predicted by the trained neural network. They have applied this approach not only to the device simulation, but also to the process simulation. I expect that there will be more attempts on application of AI to the TCAD tools near future. In the last IDM, the authors of Global TCAD Solutions, a TCAD vendor, reported a design technology co-optimization DTCO approach. Of course, such an approach has been implemented also by other TCAD vendors. Starting from the layout of MOSFETs, the transistor structure is generated. Then, the device simulation is performed to get the electrical characteristics and parasitic components. By using the efficient noise calculation method proposed by Professor Bonanni, sensitivity of devices to the parametric fluctuation is estimated. Also, from the SRAM layout, parasitic components are extracted. Combining them all in the SPICE level, they can predict the performance of SRAM. Two different device options, gate-all-around nanosheet and FinFET, are compared at 3 nanometer technology node. This approach is quite popular in these days. Okay, these are selected papers for lecture 10. Before wrapping up, lecture 10, I wanted to make some comments. For the mainstream logic devices, it is difficult to boost the performance up only in the device level. Therefore, as I discussed in the last slide, the DTCO approach becomes a standard way. One important thing not covered in the lecture is the process research using the DFT. Practically, it is very important to understand the physical mechanism behind a given fabrication process. Finally, we need new simulation capabilities. Whenever a brand new simulation methodology is suggested, its impact is huge. In order to meet ever-increasing demand on the TCAD simulation, improvement of the way how we work is required. Thank you.